Welcome back to Discovering Geometry with Mrs. Berry. This is Lesson 10. Today we will be talking about inductive reasoning and patterns and deductive reasoning. This is the beginning of Chapter 2. When you were a child, you experimented with the natural world around you. You learned how to walk and talk and ride your first bike, all by trial and error. That kind of figuring out is inductive reasoning. It's the process of observing data, recognizing patterns, and making generalizations about those patterns. Other examples besides pedaling your bike or learning to walk would be figuring out which way to turn the faucet handle to make the water come out. Geometry is rooted in inductive reasoning. In ancient Egypt and Babylonia, geometry began when people developed procedures for measurement after much experience and observation. What kind of jobs do you think today that people use inductive reasoning? Perhaps engineers using procedures to build canals, reservoirs, or even the Great Pyramids back in the day. What about assessors or surveyors that use these procedures to calculate land areas and to reestablish boundaries? Throughout geometry, we will use inductive reasoning. We will perform investigations, observe similarities and patterns, and make discoveries that will help us to solve problems. A conjecture is a generalization made using inductive reasoning. For example, a scientist dips a platinum wire into a solution containing salt. That would be sodium chloride. She passes the wire over a flame, observes that it produces an orange-yellow flame. The scientist tests some other solutions. Each of them contains salt and also produce an orange-yellow flame. She doesn't find one counterexample. The conjecture made would be if a solution contains sodium chloride, then in a flame test, it produces what color? That orange-yellow flame. So sodium chloride will produce an orange-yellow flame. That is the conjecture made after this experiment. We will use inductive reasoning to make discoveries in math. We can observe a pattern and see if we can make a conjecture about how the pattern is developed. Let's use our knowledge and find the next few terms. So our pattern is 2, 4, 7, 11. What kind of pattern do you see? Well, if I look at the difference between them, what am I adding here? So between 2 and 4, I'm adding 2. Between 4 and 7, I'm adding 3. Between 7 and 11, I'm adding 4. Well, this seems like a logical pattern. If I go on to add 5, 11 plus 5 is 16. And then I would be adding 6 and getting 22. If I add 7, I would get 29. So that's the next 3 terms of this sequence. How about this new pattern? Our sequence is 1, 1, 2, 3, 5, 8, 13. This one seems a little odd, but let's look at the difference between these two numbers. I have a difference of 1. And the next one, I also have a difference of 1. Here I have a difference of 2. Here I have a difference of 3. Here I have a difference of 5. I don't necessarily see a pattern up here, except that it matches our pattern down here. What if we add these two numbers to get the next one? 1 plus 1 is 2. So then I add 1 plus 2, and that gives me 3. 2 plus 3 gives me 5. 3 plus 5 gives me 8. 5 plus 8 gives me 13. Now I can see this pattern. So 8 plus 13 gives me 21, 13 plus 21 gives me 34. 21 plus 34 gives me 55, and so on. This is actually a very unique pattern in math called Fibonacci's sequence, and you will use it again in Algebra 2 as we start to expand binomials. Now on to deductive reasoning. We may have made many conjectures over the years, and they may all be true, but we may not have been able to explain why they were true. Deductive reasoning is the process of showing that certain statements follow logically from agreed upon assumptions and proven facts. So this is what lawyers are doing when they come in and make a case in the courtroom. They're going to pull upon proven facts, and they're going to follow logically to prove certain things. So we use deductive reasoning in algebra. You use logical steps in your process as you solved an algebraic equation. You could provide a reason for each step that you took. Let's look at this example. Right here, as we're trying to solve this problem, we have what is given to us. And then we're going to go ahead and distribute this 5. So when we do that, we've used the distributive property. And then as we start to solve for x, I'm going to gather like terms. So I'm going to, add this 3x to this side. So I'm using the addition property of equality. I added the same thing to both sides. And then I want to move this 10 over, so I'm going to subtract it on both sides. So now I'm using the subtraction property of equality. And then I want the x by itself, so I'm going to divide both sides by 8. I'm using the division property of equality. And when I do that, I get down to the answer of x equals -2. Let's try that ourselves in the next problem. First, we have our given equation. And then what do we do from this step down to the next one? I'm going to subtract that 3x on both sides. So the subtraction property of equality. And then what am I going to do here? Well, I want to move this 18 over to be with the 2. I'm going to add 18 to both sides. So now instead of subtraction property of equality, it's the addition property of equality. And now I want the x by itself, so I'm going to divide both sides by 2. And I get down to x equals 10, so I use division property of equality. And I was able to solve that x equals 10 from these logical steps that I already knew. We can also use deductive reasoning in geometry. In each of these diagrams, the ray AC bisects the obtuse angle BAD. We're going to classify the angle BAD and the angle DAC and CAB as either acute, right, or obtuse. Then we're going to come up with a conjecture about this pattern. So what do we think this one is right here? We have BAD, and this one is 120. So BAD is going to be obtuse. And then what do we think of BAC and CAD or DAC? These two both look acute. All right, BAD and this one is 158. It's definitely obtuse. And how, when I divide it, are DAC and CAB? Well, they both look acute. Though pretty close to 90, I bet that's not, right? I don't see it being 90 degrees. How about this one? BAD is 92. It's an obtuse angle. And what do we form? Again, we form two acute angles. So what is our definition of angles? Remember, we said the shortest way to measure between one end and the other. So in this case, all of BAD, each of these BAD examples, we're going to measure between 90 something and 180. Right? We couldn't measure more than 180 because that wouldn't be the shortest way around to measure it. And we said that there are obtuse angles, which means they're going to be more than 90 degrees. What is our definition of obtuse angles? More than 90, but less than 180, based on our definition of angles being the shortest way around. And if a ray bisects an angle, what do the two resulting angles become? Well, if we're dividing something between 90 and 180 by 2, what does algebra tell us the answer has to be? It has to be between 45 and 90 degrees, but not touching either of these, right? Because it has to be greater than 90 and less than 180. So we'd have to be greater than 45 or less than 90. Well, 45 degrees to 90 degrees, not quite touching 90 degrees, must be acute. If we divide the smallest obtuse angle in half, we get 45 and something. The largest obtuse angle in half is going to be less than 90. So by our deductive reasoning, we will always form two acute angles when we bisect an obtuse angle. That would be our justification in this reasoning. We looked at all these pictures, we saw that they were all acute, and then we used our deductive reasoning to prove why they would always be acute when you bisect an obtuse angle. That's it for this lesson. See you next time.